Hi, so we're going to start with linear kinetics now. And so I just want to remind you that we've been doing kinematics in the course previous to this, which is the description of motion, no indication or no analysis of the forces or torques that cause the motion. And now we go into kinetics, unfortunately, very close in spelling to kinematics, but kinetics deals with forces and torques. So we're entering a new era or a new arena of the biomechanics area. So kinetics are the source of movement, and this is where Newton's laws are housed. I've taken you to a few of the NBC Learn videos. I encourage you to review them. They're excellent, and we're going to look at a few of them in class. So the first law of inertia, states a body continues in its state of rest or constant velocity unless an external force acts on it. So something just sits there or goes at a constant velocity unless you have some sort of force that would cause an acceleration. And this concept of inertia is proportional to mass. So what is inertia? Inertia is basically the resistance to change in motion. It's directly proportional to mass, as I said. And so if you look at these two images, a sports car and a big tanker, which one has the most inertia? It is the tanker because it has a bigger mass. It is much harder if you slam on the brakes to stop the big boat than it is to stop the lightweight sports car. So let's look at mass. Mass is a quantity of matter and its units are kilogram. Density is mass over the volume. Okay, so it tells you how much mass is packed into a volume container. So size doesn't completely dictate inertia, right, because of this concept of density. And we have two comparisons, right? So here we have a bowling ball and a volleyball, both the same size, but very different inertias, right? So if I were to throw a bowling ball at you, it would create you would have to exert a larger force to stop its motion than if I threw a volleyball at you. And that kind of gets into medicine balls too. That's why they are a training tool, is because they increase the inertia by increasing the density of something that's a very similar size to a standard sports ball. All right, the second. And let me just give another example of inertia. This gets into the concept of how you would choose if you were on the executive, part of say a football team. How are you going to pick the front linemen? Right? One of their features is going to be they are going to have a large inertia. So they're going to have a large size, and hopefully packed with muscle, which is fairly dense, so they are able to impede the movement of the people coming at them because of their large inertia. All right, law of acceleration, and this is the one, Newton's law, probably that most of society is familiar with, the F equals ma. This relates to the quantities of force, mass, and acceleration. And we discussed this briefly just when we were talking about accelerations, and I asked you to think of accelerations as pushes, similar to a force, and it's because of this relationship. The relationship of force and acceleration and mass kind of modifies that relationship. So force is proportional to acceleration, and here's the equation, which we're going to derive this equation into a much more, from my perspective, useful equation to look at movement. Okay, so here's a question. What is the advantage to Apollo Ono losing 20 pounds? And this actually happened between, I'm going to get my dates wrong, the 2002 and 2006 Olympics. Hopefully you guys remember Apollo Ono, very, very well decorated short track speed skater, obviously very fit. The first time he was in the Olympics, and he had tons of medals, but he decided to lose 20 pounds. So what is the advantage? So here are our options. One, he decreased his mass so he can decrease his force, right? So we're looking at the F equals ma. You can increase your acceleration if the force is constant, right? So that's if your force is constant. So let's go back. If force is constant and you decrease that mass, you're going to increase acceleration. That looks good. Decrease mass, decrease acceleration. Hopefully not, although there is a way that this could occur. And decrease muscle mass. Again, 3 and 4 kind of link in together. So by decreasing his mass and maintaining a constant force, which is the key, he could increase his acceleration and then increase his velocity and go faster. Now, you would probably want to keep a close eye on how he's losing this weight, right? You would want to lose body fat, obviously not too much, where you would get into health issues, but you wouldn't want him to lose muscle mass, or at least enough muscle mass to affect muscle force and then joint torque capabilities. All right, so let's go back to kind of think through the law of acceleration. So you create a force on some sort of object, so you're kicking a soccer ball. It increases the acceleration. That increase in acceleration will result in a velocity, as we've seen with previous examples. And that increase in velocity will result in a change in displacement, which is typically what we want in motion. It just depends if we want a linear change, an angular change, etc. And all of this is dependent on the mass of the object. So force results in the acceleration of an object. And here is this slide just in text if you need that. A force on an object results in an acceleration of the object. The mass affects this acceleration. The acceleration results in a change in velocity of the object and a resulting change in the displacement of the object. So that is our law of acceleration. Okay, to finish up, or to kind of take the law of acceleration to another level, we do some basic mathematical manipulation. So F equals ma, so the force equals mass times acceleration. Acceleration, it can also be written as a change in velocity over time, right? If you refer back to our kinematic lectures. So force equals mass times the change in velocity over time. If you divide both sides by time, you end up with force times time equals mass times velocity. And then that introduces us to two new concepts, and the concept of impulse and momentum, which I think are much more interesting when you're looking at human movement. So impulse. Impulse is force times time. And that is typically what we think about when we think about somebody striking the ground, striking, say, with a punch an object. We typically say, oh, the force was really high, but it's technically the impulse, because you do not apply a force in an instant, right? You apply it over time, and it's that force over time that creates the movement. So our ground reaction force is very inappropriately named, because the ground reaction forces, which we saw in the force lecture, are actually ground reaction impulses. Because if you remember the graph, it is force on the y and time on the x, so it's an impulse graph. In football, okay, so this is another kind of silly view of impulse. If this player applies force for a long enough time, they will stop the momentum of the offensive player, right? So either they can hit them with force over time, or they can just hold on and apply their body weight over a long period of time, get dragged across the field, and eventually, potentially, stop this player. And this is also the ground reaction force, but it's technically an impulse. And here are examples of walking ground reaction forces. So the ones I introduced in the force lecture were for running. And if you remember, they looked kind of like Michigan, like a mitten. This is a standard textbook example of a walking ground reaction force or ground reaction impulse. And so you have your little heel strike transient, and then you have one pulse that goes with the braking force, one increase in force that goes with the propulsion force, and then you have this little unweighting period, where you kind of flex your knee at mid-stance. All right, and here's our typical running one. So you have a heel strike transient depending on how you strike the ground. This is a heel toe runner, and then you have the braking force and the propulsion force, and then just one big force that in the vertical direction that propels you forward. Here are some ground reaction forces that actually go with the data that you've been looking at each joint. This was the same runner. So this was at a normal speed. We had them run over the force plate, and this is their force production. Now, force is in newtons. So I challenge you, if you had, say, a 70 kilogram male, how many times body weight are they striking the ground with each step? Okay, so this is one step, right? They're engaged with the ground in the vertical direction. Their peak is about 2,200 newtons. If they are 70 kilograms, how many times body weight are they impacting the ground with each step during running? And remind me in lecture and we'll review that. So here's the AP shear, or the propulsion and braking force. So you have the braking force, right? So this is acting to impede the forward motion of the runner, and then they go through mid-stance, and then they propel themselves forward. And we discussed that walking and running is a series of braking, propulsion, which is basically a series of almost falling and then catching yourself. Here's a fast ground reaction force. So you can compare this to this one. So we see this took about 0.2 seconds. This one took almost a little over 0.1 seconds. So they're engaged with the ground in a much shorter time frame. But then look at these two peaks. This peak increased a little bit, right, to almost 2,500, but you had a significant increase in the heel strike transient. And so again, you should calculate for a 70 kilogram male, what times body weight is being kind of transmitted through their body with each strike. And here's the braking and propulsion graph for the same runner in a fast. So they had a 600 Newton force applied against them. And so let's compare that. The heel strike was about, or transient was about 600, but the main braking force was in the 500, so it was a little lower. Their propulsion force was about 400 for the normal speed running. And let's see what it was for fast, which makes sense. You would assume the propulsion phase in the AP direction, if you're going faster, should be increased to increase that running speed, and it is from, it was about 400 newtons, and it increased to about 600 newtons. All right, and then we're going to finish up this segment with momentum. So that was the impulse side. All these graphs described a force and a time. And then it results in a momentum. And people, in my opinion, misuse the word momentum all the time. So we're going to be very precise about how we use momentum. And it's also used in the American Ninja Warrior a lot. Sometimes correctly, sometimes not so much. So you guys will be analyzing that. Okay, so momentum, the definition is it's a quantity of motion. And momentum, the equation is mass times velocity, right? So you've applied an impulse, and then the mass that you applied the impulse to moves at a certain velocity, and that mass times velocity is considered the momentum. All right, so let's we'll keep going until law of reaction. Okay, so let's talk through this. I like to think of motion as impulse, momentum, and then impulse. And that's, for many of our sporting activities, we apply an impulse to the ground, we hurl our bodies through space, So that's the momentum, and then we land on the ground again with an impulse. And that can create a lot of injury, so this impulse becomes very important. So a few examples. Long jump. You apply a force to the ground, you go through the air, and then you land on the ground again. A baseball throw and catch, right? So the first thrower applies an impulse to the ball has momentum and goes to the next person who catches it, and that ball creates an impulse on their glove. Shoes, impulse momentum ideas. So shoes, we apply a ground reaction force, right, as we're running each step, and then we hurl our body through air, so we have the flight phase, which is our momentum, and then the shoes are meant to affect certain features of that impulse on landing. And so let's think about midsole materials in shoes, the idea of crash pits, right, the big mats in gymnastics, sand pits at the end of the long jump, gloves in baseball. Why do we have these? And typically we start with an impulse, so force times time, and then either your body, the ball, whatever's being transferred through space has a momentum, so it's mass times velocity, and then then at the other end it lands. So take the long jump. You're hurling your body through the air and then you land. Do you want to land on concrete, or do you want to land in a sand pit, sorry? And if you land in the sand pit, you have the ability not to change the magnitude of your impulse. That is constant. But you have the ability to alter the force and the time over which that force acts. So once you leave the ground and go hurling through the air with a momentum, you cannot change this impulse that you will experience when you land. But what a sand pit does is it increases the time over which this force will act. So if the impulse is constant and you increase time, you will decrease the force. And so the force applied to your body will be decreased, thus potentially decreasing injury. For a baseball throw, you create an impulse, the ball goes hurling through the air, and then somebody on the other end has to stick up their hand to try to catch the ball. And if it were me, I would want a nice big baseball mitt, because the impulse is going to be constant, and that mitt increases the time, and so it decreases the force. And you guys can all try that, right? If you catch a ball without a mitt, it's going to hurt more than with a mitt. And what else do people say? Catchers, in baseball, what do? Typically, they kind of flex their elbow joint and kind of give as they catch. And that give also increases the time, so it decreases the force. All right? And here we have just in visual. So you have an impulse, you strike a force times a time, you have momentum through the air, and this is linear momentum, right? So all this movement of your arms and legs has nothing to do with this linear momentum, the mass times velocity. But at landing, if there's a sand pit, you can increase time, which will decrease the force, which will save your legs a little bit. Here's another example. So here are two ground reaction forces, okay, A and B, and this is the knee joint kinematics for both of the A scenario and the B scenario. So my question to you is, which jumper reached a greater height, A or B? Okay, so here we have a few things. So A, here's the knee joint angle of flexion extension. They reached a much higher knee flexion angle than jumper B, right? They reached a little over 60, sorry for the numbers. These guys reached almost 120. So that was a bigger counter movement, if you will, than in A compared to B. And how did that translate over to the vertical force? So here they're standing on the force plate, they unweight a little bit with the counter jump, and then this is the force they apply before they jump off the force platform. So this has a bigger impulse, a bigger force times time. It also reaches a higher force, and the bigger impulse will result in a greater momentum, mass times velocity. And if mass is constant, if you increase that velocity, you become a projectile, and if you increase the takeoff velocity, you will reach a higher height. All right, so greater knee joint angles create a bigger counter movement, which creates a larger force, which creates a larger impulse, which creates a larger momentum, which creates a larger initial velocity, which results in a greater jump height. And we're going to stop there.